Hi everyone, my name is Fatima Ezzeddine and I will be presenting today the poster presentation of the topic of towards preserving counterfactual explanations. The outline of today's presentation is the following. I will start by defining the AI field, the explainable AI field, with focusing on the counterfactual explanations, and then I will be discussing the privacy and explainability at play. And then I will be presenting our proposed methodology, SACFACT, which is represent the soft actor critic reinforcement learning for counterfactual explanations, with showing some numerical results, some evaluations, and the convergence analysis of the proposed methodology. And then we will end up with a conclusion and the future work discussion. Starting by defining the explainable artificial intelligence. First, explainable artificial intelligence will provide explanations of why the specific machine learning model have made a specific decision. So it will help us understand the output of the model that we have in order to build the trust, to enhance the transparencies of the model's output, to understand the reasoning behind the model that we have, why it's making a specific decision, why our model did not consider an alternative option, what are the conditions where I can trust my model, what are the failures when failures are happening, why a decision output was made and why not another one. So this type of explanations that are made by explainable artificial intelligence in order for an end user or a data scientist or any person that is trying to understand the output from his own perspective, to understand the decision of the machine learning model that is being explained. Like, we have different types of explainable artificial intelligence, but in this presentation I'll be focusing on the post-hoc explainability. Like, we have pre-hoc and different other families of explainability. Like, what we mean by post-hoc is that when we have already trained machine learning model and we are trying to understand the output of this model, this is what we have, like the post-hoc. We already have the decision, we already have the model, and now we want to understand why this model made this specific decision. So we have the training phase and the explainability phase. In the explainability phase, we can have a global explanation, which is an explanation of the whole model, how it's functioning, the reasoning behind it, and across a global view, the explanation. While in local, we are trying to explain a specific instance or a specific decision, and basically this is it. And these explanations will help us debug the model, the output, in order to improve, to discover fault, discover how to be trust, to control some decisions, to make some justifications of some decisions. So this is the main idea. But some frameworks of explainability that can help different types of explanations. Some of them can give us the features importance. For example, what are the features that are mainly important for the decision, what are the mostly affecting our decision. We can have counterfactual explanations, which features to change in order to have a different output. We will see this in the next slide. We have Synapse, we have other visual explanations that we can have. For the counterfactual explanation, which we'll be focusing on in this presentation, like, a counterfactual explanation is basically a hypothetical scenario which we want to explain a specific data point by giving some actions and some explanations on what features to change in order to get into another class, from changing, for example, from class A to class B. And this can help us detect unfair outcome and have strategies on how to alter or change the decision for future uses. For example, a person who had his loan rejected wants to know what are the features what he should change and what he should alter in his behavior or his feature in order to get his loan accepted. And also, maybe we want to detect and we want to have justification to detect wrong decision. If we have fault reasoning, this is all how counterfactuals can help us. So the main idea is that we want to cross the decision boundary of the machine learning model that we have and changing the output from class A to class B by having different objectives and different properties of these counterfactual explanations, which are we want them to be similar as possible to the initial instance. We want to have minimal changes in the number of features, we want to have multiple scenarios, multiple counterfactuals, and have diverse way of changing the output, the features, in order to get the output, to change the output. And also, we want to have valid counterfactuals. We want to have in distribution features. We don't want to have unrealistic counterfactuals that does not come from the distribution of our dataset. Different methodologies have been proposed to generate counterfactual explanations. Some of them are based on the mixed integer programming and some heuristics. Some of them are based on the meta-heuristics algorithms. But for generating counterfactual explanations, we have some of them are limited to the internal structure of these black box models. The black box model is the model that we want to explain because it's said to be black box since we not fully can understand the reasoning of how this model is working. It's a complex computation, and some of them are optimizing a single metric, some of them are applicable to some binary classifiers, and some of them have other limitations. In this presentation, we want to shed the light on reinforcement learning and how it can be used to generate counterfactual explanations, since it has not been thoroughly explored, and when it is explored, it's been mainly applied to specific scenarios where for specific use cases, and it's not generalizable to any type of dataset. So how RL can be used to generate counterfactual explanations that can be made, we can think of it as an agent who is searching through the space to find an optimal policy to transition from a specific class to another class, which is the counterfactual explanation. So RL gave us the strategy or the trajectory in order to achieve our counterfactual explanations, to extract it. And RL is mainly important in this type of use cases, since RL can handle complex constraints and explore large search space. And in our work, we'll be focusing on the soft autocritic algorithm, since it's well known to balance exploration and exploitation, and by handling high-dimensional state spaces. For example, when we say by balancing exploration and exploitation, we have an agent that is exploring the state space to learn how to behave, how to achieve its goal, and by exploiting it or earning it, which is the optimal solution, which in our use case, which is more to generate the counterfactual, it will be the changes, the increases by the feature, decreases by some features. It can be any type of modification that the model should exploit to generate a counterfactual that we want and to cross the decision boundary from the class A to a class B. But everything comes with a price of something. So for explainability, we have explainability frameworks, which are counterfactuals, and other than counterfactuals are trying to give information about the model reasoning, how the model have made its own decision. And this way we are giving information about the model that we have. We are maybe unintentionally we are giving information about the sensitive data that the model was trained on, and this comes in contrast with the concept of privacy, where privacy is trying to limit the disclosure of any data or any information or any property of the model that we have. And there is different acts that are discussing this requirement, the privacy requirement, like the GDPR or a lot of acts, many other acts, and this is causing a trade-off between, like, we want to explain our model and we want to hide information as much as we can to not leak any information or any property about our data, and specifically that these type of explanations are being used by various attacks to attack the machine learning models and to extract information from these models. Example of possible attacks: the membership attack. It's an attack that can determine whether a specific data point was part of the training dataset of the machine learning model that we have. And the inference attack, it can infer sensitive attributes, sensitive properties, and by analyzing the output of the machine learning model, and also by analyzing the output of the explainability of this machine learning model. So explainability output is being used to attack machine learning models in different use cases. So our proposed methodology is the following. It's called SACFACT. It has the objective of developing a privacy-preserving and model-agnostic scalable counterfactuals generator that can output counterfactuals explanations and does not require the training data points as an input. Why we are saying that it does not require the training data point as an input? Because for most of the counterfactuals explanations, methodologies, they require the dataset as an input, and they do their optimization based on this training datasets, which is having as an output counterfactual that are very close to the training dataset, which is this is a way of revealing the informations in these counterfactual of these datasets to anyone who is trying to explain or attack a model or leak any type of information. So the SAC-FACT, which is soft active critical reinforcement learning for generating counterfactual explanations, SAC-FACT distinguishes itself from other methods that does not take the training data as an input. It takes as an input a trained model and the instance to explain on it without the training data points. SAC-FACT will give as an output which feature that we have to modify, and with each feature how much we should modify it. So it gives us as an output the action space is the feature and the amount to be changed in this feature. And about the reward function, reinforcement learning will try to maximize the reward function, which we customize it in order to optimize various metrics that are by describing the requirement of counterfactual explanations. Also, in order to get diverse and valid counterfactual explanations, we employ anomaly detection through isolation forest and the reward function in order to let the reinforcement learning learns to avoid anomalous counterfactuals and to give valid output. So in simple terms, we have SAC-FACT that take as an input the black box model, the instance to explain, and give as an output the counterfactuals that are optimized and generated during the training process. In this proposed methodology, we are trying to answer some research questions, which are how does the proposed counterfactuals explanation generation method will compare to existing approaches that rely on the datasets as an input, and also what are the implications when we have a model not trained on the training dataset but trained on synthetic datasets. We want to quantify and explore the effect on the explanations itself when we are training it with synthetic datasets. So the proposed methodology is the following, but we want to, in terms of reward function, we want to have non-anomalous data points and optimal counterfactuals, which we mean by changing the minimum number of features and to be closest in space. So in terms of reward function, the reward function is customized to account to other requirements to generate counterfactual explanations, such as the Hamming distance, the Gower distance, the anomaly penalty, the minimum number of reinforcement learning steps, and how to achieve the goal. So in this way, we are covering all the requirements of generating counterfactual explanations in the reward function that should be maximized by the reinforcement learning, the soft actor critic, during the training phase. In terms of evaluation settings, we have tested SAC-FACT on 4 public datasets are trained with the gradient boosting algorithm classifiers, and we have varied the number of features in order to test the scalability of SAC-FACT. We have datasets from 8 features and datasets with 41 features. Also, we have compared up to some baselines such as DICE and single CF in order to compare the performance of these 2 models that they do require the training dataset as an input, while SAC-FACT do not require it. In terms of evaluation metrics, we are comparing the sparsity, the proximity, and the validity of the counterfactuals when also in 2 scenarios where the data is preserved and where the data and the model are preserved. The data and model are preserved, we mean this by having the synthetic data set model that traces on the synthetic. In addition to this evaluation, we have analyzed the convergence of the SAC-FACT. We have made some plots about the rewards function, how it's been maximized, the entropy, and this type of analysis. So we start by the baseline approaches comparison in terms of the scenario of the data preserved, and in terms of proximity specifically, we can see that SAC-FACT is outperforming DICE and the single CF, and that the counterfactuals that are generated by SAC-FACT are close to the original data points, and also the same in terms of the best optimal counterfactuals that are very close to the original data points. While in terms of sparsity also, we can see that SAC-FACT is outperforming DICE and single CF and have fewer modified features compared to DICE and single CF. Also the same for the optimal counterfactuals that have very few modified features. In terms of validity, since we have added the penalty of anomalies in the reward function. We can see that also we have high validity scores over the 4 datasets, and have that the reinforcement learning have learned how to avoid generating anomalous counterfactual explanations. In terms of SAC-fact, that is in the scenario of data and model preserved, we have also in terms of proximity, we can see that the results and the proximity have remained consistent across both the real and the synthetic datasets, while preserving the identical spatial distances. Also, it's the same in terms of proximity. We can see that we have remained consistent in terms of the number of features that are being modified in the counterfactual explanation. This means you have preserved the quality of the explanations with the synthetic datasets. In terms of the convergence analysis, we can see for the 4 datasets and these wireless plots that the convergence time steps is differing over the datasets, because we can say that the higher the number of features, the more time steps are required to convergence. And also we can see that SAC-fact has an acceptable convergence rate independent of the number of features that we have. In terms of convergence of the algorithm, we can see that this is an example of a single model of a fact. We can see how the reward is being maximized over the time steps, which is what the goal of reinforcement learning is. And also, in addition to the exogenous mean, which is being minimized, minimizing the number of steps to be made in order to achieve our counterfactual. And also for the entropy coefficient, which is a requirement which is being optimized also during the training of the SAC-fact algorithm theoretically. Also, we can see that it is being maximized over time, which is following how SAC-fact critic itself works and should work. And this is how we can see that this is a proof that SAC-fact is really converging by seeing the plots, by analyzing the plots, and these convergence plots. As a conclusion, we have proposed SAC-fact, which is a novel approach based on the SAC-fact critic reinforcement learning that does not take into account the training datasets as an input, and it's following the main guidelines for generating counterfactual explanations by accounting them in the reward function. Also, we can see that SAC-fact is surpassing the baselines and biasing single CF over the 4 datasets. Also, we have, while demonstrating the convergence. In addition, we have discussed the privacy and explainability interplay in terms of counterfactuals, and we have shown how SAC-fact can address it, such as preliminary results in this presentation. For future work, we aim at generating privacy-preserving counterfactuals with, for example, differential privacy to have more private counterfactuals. Also, we have more to explore strategies to accelerate the convergence of the SAC-fact critic. Also, we can improve the quality of the generated counterfactuals on classification, regression, or clustering tasks. So feel free, this is all, so feel free to send me an email if you have any questions or any doubts or will not have any discussion. This is my emails. I'm always happy to answer your questions or to have any discussions. So thank you for listening.